In this tutorial, we are going to discuss the Bohr model and its relationship to light. First, we'll talk about how Bohr's model works, so how it's organized and why he came up with this new model. And then second, we'll talk about how light is actually emitted by electrons from an atom. And then third, we will talk about what an atomic spectrum is. So before Bohr, you'll remember, there was Rutherford, and Rutherford's model had, the nucleus in the middle, and then he just said the electrons just kind of orbited wherever around the atom. And he didn't really say much about where the electrons were orbiting, and Bohr thought that that wasn't a decent enough explanation for an atom, because Bohr and other scientists noticed things like that when you burn copper, that copper always burns green, or sodium always burns orange, and strontium always burns red. And they thought that was odd and wanted an explanation for that. And so Bohr worked on a new model. So this is Bohr's model of the atom. And Bohr's model of the atom is different from Rutherford's because, well, it's the same as Rutherford's because there's a nucleus, but it's different because Bohr reasoned that for atoms of, say, copper or sodium or strontium to always, when heated, give off a particular color, or when reacted with other chemicals to always have the same reaction, their electrons must be more organized than what Rutherford said. He said that these electrons are organized in energy levels that have fixed distances from the nucleus and fixed pathways, and that the electrons orbit in those pathways. And that all these electrons that are in each of these energy levels, they're there because of the amount of energy that the electrons contain. And so he said that there are lower energy levels closer to the nucleus, and that the further away you get from the nucleus, the electrons have less and less energy. So are more and more energy. So they're higher energy levels the further you get from the nucleus. And remember, his reasoning behind this was because, well, number one, electrons or certain elements always react a certain way with other elements. So whenever you mix, say, sodium with water, it reacts super violently, and it does that every single time. And secondly, he noticed, and a lot of other scientists noticed, that whenever you burn these elements, they burn very particular colors. Copper always burns green, sodium always yellow, strontium always red, magnesium always burns white. The Chinese have known that actually for a very long time. They didn't have an explanation for it, but they've been using that particular quality of atoms to make fireworks for a really long time. Okay, so let's explain Bohr's model a little bit more. Okay, so on the left here, I've drawn the best model of a Bohr's model that I can. And then on the right here is a picture of a ladder and the energy levels. So just so that you know, Bohr said that there are an infinite number of energy levels, and he designated energy levels with this letter N. So first energy level, he said, is called N equals 1. And then the second is N equals 2, and then N equals 3, etc., and that you can have infinite numbers of energy levels. And you might notice, so of course the nucleus is in the middle, and then energy level 1, N equals 1, energy level 2, N equals 2. N is called the principal quantum number, and that just means energy level. So don't get confused. If I ever use the words principal quantum number, what I really mean is just energy level number. All right, so he said that electrons fill the lowest energy levels first. So, well, he didn't actually say that, but he said that, once an energy level is occupied, then electrons will go to the next energy level. They'll fill that up, and then the next energy level. And then in theory, you can have an infinite number of these. So what I have over here is a picture of those energy levels just kind of flattened out. So this is N equals 1, this is N equals 2, N equals 3. And he said that the energy levels were a lot like the rungs of a ladder, meaning that if you have an electron that's orbiting in N equals 1, that it was, so I'll draw it on the ladder and also in the energy levels, that those electrons were capable of getting excited or absorbing energy and jumping up to a higher energy level. And we'll talk about what that means here in a second. But the point is that if energy levels are like the rungs of a ladder, just like you can't step between rungs, electrons can't exist between energy levels. They have to exist in an energy level. They can't exist between energy levels. And you'll notice also that the electrons, or rather the energy levels, and I try to draw that in this picture, get closer to each other. So the energy levels get closer as you go further out from the nucleus. And so you can see that up here as well as how I drew it in my picture. So unlike the rungs of a ladder, which are evenly spaced, energy levels actually get closer and closer and closer to each other as you get further from the nucleus. And the reason that they actually get closer together isn't because they physically, in real life, are actually closer together. We draw it this way to represent the fact that the further an electron gets from the nucleus, or the further an electron orbits from the nucleus, the less energy or the less attraction it has to the nucleus. So you have an electron way out here in energy level 5, right, in n equals 5. Its distance from the nucleus is less than the distance from, say, n equals 1. And that means there's less electromagnetic force pulling on it from the nucleus. Remember, electrons are negatively charged, right? They have all these little negative charges, and the nucleus is positively charged. And so the further an electron gets from the nucleus, the less pull it's got on it. And so that means that if the energy difference between, say, an n equals 5 and an n equals 4 electron is far less than the energy difference between, say, an n equals 1 and an n equals 2, just because of the distance from the nucleus. Okay, so that's Bohr's model in a nutshell. And let's talk about how light is emitted from an atom or by its electrons based on what I just showed you on Bohr's model. All right, so here's a picture of Bohr's model drawn by me. It's lovely, I know. All right, so here we have n equals 1 electron. So we have an electron orbiting at n equals 1 in what we're going to call its ground state. So a ground state is an electron in an energy level that it would normally exist in, right? That it's at its normal everyday kind of energy state. Now, let's say that electron gets hit by some sort of energy. And that energy can take a number of forms. It can be a higher energy kind of light, like ultraviolet or heat or something like that. It can be fire, it can be electricity. So we've somehow added energy to that electron. Well, that electron, like you, can get excited. So, think of like when you drink caffeine or something like that and how you absorb energy and you get excited. So that ground state electron can absorb that energy and get excited. And when it gets excited, it can jump up to a higher energy level. And that higher energy level is called its excited state. So it wasn't its ground state, it absorbed energy, it jumped up to an excited state. So again, a lot like you with caffeine, you drink that caffeine or sugar and you get excited for a little while, but just like you, it can't exist in that excited energy state forever. In fact, for an electron, it's just a blip of a second. And so it's going to fall back to its lower energy level and releases that energy as light. Every time. So electron absorbs either light, heat, or electricity. It jumps up to a higher energy level, and then when it falls back down, it releases that same amount of energy as light. A couple things you need to remember about this process is that electrons cannot jump between energy levels. Just like you can't step between the rungs of a ladder, electrons can't jump up and exist in between energy levels. You also need to remember that an electron, for it to jump to a higher energy level, it needs to absorb exactly the right amount of energy to get to that higher level. So again, just like you stepping up to the rung of a ladder, you have to lift your leg a certain height or put enough energy to get it to that next rung. And electrons are the same way. And by the way, that amount of energy has a name. It's called a quantum. And a quantum of energy is not, there is no number that goes with a quantum. A quantum of energy just means an exact right amount of energy. So I like to think of it like a packet or a parcel of energy, like a little sugar packet that you would get at a restaurant. That little sugar packet is a parceled out amount of sugar. And that's what a quantum is. And remember, from over here when we talked about Bohr's model, a quantum of energy to get you from energy level, say 2 to 3, that quantum of energy, that exact right amount of energy is going to be different than a quantum to get you from, say, 5 to 6, right? Because the energy levels get actually closer in energy to each other the further you get from the nucleus. But we'd still call each one a quantum because it just means the amount to get you from one energy level to the next. That's what a quantum of energy is. All right, so we're back over here talking about the things to remember. All right, second thing, the third thing you need to remember is that electrons will always release the energy that they absorbed as light when they fall back to their ground state. So it doesn't matter if they absorbed light, heat, or electricity to jump up. Every time they fall back down, they'll release light. And remember, not all kinds of light are visible. And then the fourth thing you need to remember is that the amount of energy absorbed by an electron, so if they absorb 2 joules of energy, they will always release the exact same amount when they fall back to their ground state. It's just that they always release it as a form of light. They don't have to absorb it as light, but whatever it is that gets released, it's going to be some kind of light. Remember, light isn't always visible. There's a lot of kinds of light that are invisible. So you can think about when a spoon gets warm. You put it in a cup of tea and it absorbs heat, and then it gets warm and it will release that heat. And remember, heat is infrared radiation. So that's a kind of light. Or you can think of putting that piece of metal, that spoon, in a fire and it gets glowing orange, right? Because it gets so hot, it actually starts to glow red hot. That's releasing not only heat, but light, like visible orange light. All right, so let's answer the very last question that I posed, if I can find it. There it is. What is an atomic spectrum? All right, so scientists have known for a while now that when you take light and you look at it through a prism, so for example, if you take white light, like sunlight, and you look at it through a prism, that you're going to get a rainbow. That's a continuous spectrum of every visible kind of light that there is. So you've got red all the way through violet, right? Roy G. Biv. And they've known that if you take certain or all the elements and you make them a gas and then you heat them up and look at them through a prism, that they'll give you only very specific parts of the continuous spectrum or specific wavelengths of that spectrum. You can ignore this bottom picture. So this thing is called an atomic spectra. An atomic spectrum is the visible wavelengths of light emitted by excited electrons of an element. And all elements give you a very specific atomic spectrum. It's a way to identify an element in its hot gaseous state. And so down here what I have is the atomic spectrum of hydrogen. And that's what Bohr mostly worked with, was hydrogen atom. So Bohr was trying to explain the atomic spectrum. Why is it that hydrogen only gives you this one red wavelength, this one blue, and this one sort of violet wavelength? There actually is one in the green that you just don't see in this picture. So I can draw that in for you. There's like a green one kind of down here. So why is it that it always gives you those 4 wavelengths and then see in between it's missing a bunch of color. Why is it that hydrogen always gives you those particular wavelengths and nothing else? And so he used his explanation of an atom to explain that. He said that the one electron, remember hydrogen only has one electron, is capable of getting excited in all of these ways, right? So you've got it's one electron if it's in n equals 1, right? It can get excited up to the 5th energy level and back down, to the 4th energy level and back down, to the 3rd, to the 2nd and back down. So that's all the ways it can get excited. And when that happens, it actually releases a whole bunch of invisible light. So in the UV region. And then over here, he's got the same thing, and he called that the Lyman series. And that electron can get excited up into the 2nd energy level, and then from there, excited up to the 3rd and back, 4th and back, 5th and back, and 6th and back. And that's what gives you these visible wavelengths right here. And then there's also a Paschen series, which you don't need to really know, that also gives you some infrared or heat lines or heat wavelengths. So he said that all atoms, their electrons are capable of getting excited in a whole bunch of different ways, but that they always get excited in the same ways, which is why you would get the same atomic spectrum for those particular elements. And so just quickly, here are some atomic spectra for a whole bunch of different elements. So notice lithium. Lithium has a very specific spectrum. It gives you 1, 2, 3, 4, 5, 6 lines, and those are different than the lines you're going to get from, say, cesium or potassium or sodium or rubidium. And then, of course, there's this unknown spectrum at the bottom that's a mixture of some of these gases. And so you can kind of match some of the lines up and tell that this line matches that one, and this matches that, and that, and that. So you know that, we can keep going. We know that that unknown spectrum contains potassium as well as some unknown element that doesn't seem to be, let's see, nope. And also, it looks like it has rubidium in it as well, because it's got lines that match rubidium, right? So there's some rubidium. And it also looks like it might contain some lithium, because it's got the lines that match with lithium, right there and there. So it also contains lithium. So we can look at a star, for example, that's billions of light years away, and we can run the light of a star through a prism and maybe get something like this that's a mixture of a bunch of gases, and we can match those to the known spectrum of all the elements that exist in our universe or in the universe, and say, oh, that star is giving off 3 different gases: potassium, rubidium, and lithium. And so we know that that's what that star is made of. So that's an atomic spectrum. We're going to actually look at some atomic spectrum in class, or atomic spectra. All right, so that was Bohr's model of light and how it explains atomic spectra and how light is emitted from electrons.